Hello everyone, I am Ananta. I'll be talking about decidable fragments of term modal logic, and this is a joint work with Ramanujan. So let's start with first order modal logic, which we have been discussing today. So typically the syntax looks like this. We have predicates, optional equality, negation, conjunction, quantification, and we have this diamond phi. So this is basically lifting first order logic with diamond modal operators. And how would the models look like? It's a Kripke model where at every world, there is a first order structure sitting inside it, right? So for instance, at this world R, the local domain is AB, and there are some predicates which are interpreted over the local domain, right? So this is how the database, the structure looks like. Now, note that in this particular setting, if you think of diamond and box as agents, there is only one agent, right? So that in this setting, there is only one agent or there is only one index for this diamond or box. Now, very naturally, we can extend this to a multimodal setting where if you think of modalities as agents, now there are n agents. And in that case, the only change is that there is an index for this modal operator, one for each of these values, right? So for every agent, there is a diamond I and a corresponding box I operator. Now, how the models look like? The models would look more or less the same, except that earlier the edges were unlabeled, but now the edges will be labeled over this agent set. For instance, if n is equal to 2, then that is the example that is being described here. So there is 1 and 2, right? So the edges are labeled over this set 1 and 2, right? And in this case, also note that the agent set, even though is not one, many, but it's still fixed in the syntax itself. Now, there could be a lot of cases where this is not the case, right? For instance, if you think of multi-process systems where new processes are created and some old process dies and so on, we cannot fix the agent set beforehand, right? Because it keeps changing dynamically. Similarly, if you look at a client server system, there could be new clients coming in with requests, old clients going away and so on. Similarly, like large games or like voting or social networks. So these are the settings where we cannot fix the agent set beforehand, right? And in such settings, not only does the agent set change from one model to the other, but within one model itself, from one world to the other itself, the agent set will change. For instance, if you think of multi-process systems, in the current configuration of the system, there could be some processes, but once the system configuration changes, some new processes are created, some old processes die, and so on, right? So now the point is that the agent set changes from one world to the other world itself within the model, right? And in such settings, when we cannot fix the agent set, it is very natural to say, okay, I cannot pinpoint every agent, but I can quantify over them, right? So here is an example. So here we can say something like everybody knows, everybody who knows that it is raining also knows that the ground is wet, right? So we don't know how many agents are there or who the agents are, but we can still say such a property, right? So this is quantifying over the agent set, right? And this is very natural to have if we cannot fix the agent set beforehand, right? And this is the motivation for term modal logic, which was introduced by Fitting, Thalman, and Voronko, where the agency is not fixed, right? So the modalities are indexed by terms, and these terms can be quantified over. And technically, what this means is that the agent set is now the same as the domain set also with respect in terms of first order modal logic. So when I define the syntax and semantics, it will be clear. Now here is an example. So if you want to say something like there exists some process which can possibly change the system into a state where the system halts, is something like this. You said there exists X, which is a process, such that X can change the system configuration to a state where this holds. This is in some sense encoding halt. What does it say? It says for every process, the process cannot change the system configuration, right? So this is saying halt. So this says for there exists a process which can possibly make the system halt, right? So that is what this says. Similarly, in an epistemic setting, you can say something like everyone knows who killed Mary. How do you say that? You say there exists Y such that for all X, X knows that Y killed Mary, right? Note that here killed is a binary predicate, and this is a proposition, and so on. So what we are using as atoms may vary depending on the setting, but the main idea here is that we can have terms or variables for the index of modalities, and these can be quantified, right? So that is the main idea in term modal logic. Now here is a formal definition of the syntax. We have propositions, equality optionally, not phi conjunction, so there exists x phi and box x phi, right? So this is the key difference from first order modal logic. In first order modal logic, we just had diamond phi. Here we have diamond x phi, right? So what does it mean intuitively or technically? It means that the agent set that we had in first order modal logic is now also the the domain set that we had in first order modal logic is also the agent set now, right? And in terms of models, how would the model look like? It is very similar to first order modal logic models, except that the accessibility relation is now labeled over the local agent set. So for instance, here AB is a local domain, right? And that local domain also acts as the local agent set, right? So if you're thinking of process systems, then AB are the processes that are live at this world, right? And this AB are the only agents or the only processes that can change the system configuration, right? So at the accessibility relation, the outgoing accessibility relation from a world is labeled with respect to the local agents or the local domain that is live at that particular world, right? So for term modal logic, the agent and the domain are same. So throughout this talk, I'll be interchangeably using domain and agents to mean the same thing, right? So that is the key idea in term modal logic. Now, in terms of evaluating formula, you evaluate a formula at a world for a given interpretation, which says which variable is mapped to which agent, right? And you have existential formula is true at a world if you can pick a witness from the current live set, such that assigning x to d will make the formula true. And diamond x, now because we have diamond x and the accessibility relation is labeled over the local agent set, right? You say, okay, look at this x, the interpretation of x. If there is a corresponding edge labeled by that where accessibility relation labeled by that particular value, then the formula is true, right? So this is natural way to define the semantics. Now this is the logic that we'll be looking at, and we'll be looking at the satisfiability problem for this logic. Now clearly, if you look at this, if we remove this, the remaining part is the first order logic, right? So clearly the language is undecidable, right? Now the natural thing to say is, okay, now if this is undecidable, then maybe we can have restricted predicates, right? If we can we have arity, for instance, unary predicates or something like that, and get decidability, right? Now what would be a drastic measure to say, okay, I don't want any predicates at all, I'll just have propositions, right? Now not that if we have propositions, we can still have quantifications, right? So here is an example. This is, there exists x box x, such that, what does it mean? There exists an agent at this world such that for every accessible world for that agent, either P holds, or from that world, for every agent, there is a possible accessible world where not Q holds, right? So the point is, even if you have just propositions as atoms, we can still have variables and quantification over them. And these variables will be used as index for the modal operators, right? And surprisingly, at least surprisingly for us, we showed that the satisfiability problem is undecidable even with propositions as atoms, right? And the proof, if you look at it, is very simple in some sense, right? So the reduction is from first order logic with one arbitrary binary predicate, uninterpreted binary predicate. And the translation looks as follows. You take this formula, which is the atomic formula E of xy, and translate it into diamond x, diamond y top, right? And you extend it standard in the standard way for negation, conjunction, and quantification. And what you can show is that if you start with the first order formula over this predicate E, it is satisfiable if and only if this translation is satisfiable. Now, what does this mean? This means that the propositional fragment which we call PTML, propositional term modal logic, is already undecidable, right? Not that it also, from the corollary of this translation, we only used top, which is a very special predicate proposition, which is true at all worlds, right? As soon as we have that itself, the logic becomes undecidable. So this is a very restricted setting, and already there it becomes undecidable. So the question is, can we have decidable fragments for this logic at all, right? So that is a thing, that is the problem that we are going to look at. And we take the cue from first order modal logic. First order modal logic has, as we have discussed, has some decidable fragments, right? So for instance, monodic fragment, which says which says that it's restricted to the formulas where the modal formula can have at most one free variable within the scope, right? Within the scope of a modality, there can be at most one free variable. Now, Volter and Zakharyachev proved that if you start with any decidable FO like unary or two variable or guarded fragment, any of the decidable FO fragment, extend it to first order modal logic with monodic restriction, it will still give us a monodic, a decidable fragment of first order modal logic, right? So that is one. And in the previous talk, we looked at the bundled fragment. Mo told us about the bundled fragment, where some of the combinations have proved to be useful and decidable, right? So these are some of the fragments known from first order modal logic which are decidable. Now we can ask naturally, are there decidable fragments in such a spirit for term modal logic? And it turns out that yes, and the result in fact can be given in a general way, in the sense that we can translate term modal logic into first order modal logic, and this is how you would do it. So you don't change anything for predicates or any other symbols. The only problem that we would have is for this diamond x phi, right? Because this is not there in the syntax of first order modal logic, but that you can change it into diamond t of x and recursively translate phi. And the idea is that this edge label is now pushed in where, not that p is a fresh predicate, in the sense that if you start with the formula, p is not present in that. And the idea is that if you start with a term modal logic model, the edge label, whatever the value of the agent that is there, is encoded in this new unary predicate p, right? So once you have this, what you can show is that the initial formula, term modal logic formula, is satisfiable if and only if the translated first order modal logic formula is satisfiable. Now note that if you start with a bundled term modal logic formula or the bundled TML formula, what we get is a bundled or the correspondingly monodic FOML formula, right? So which would mean that as a corollary of the decidable fragments of FOML, the monodic fragment and the bundled fragment of term modal logic is decidable, right? So these are a couple of decidable fragments that we can have. Now, what about variable restrictions? We can also have something like variable restrictions and look at the decidability. Now, in that setting, I mean, if you look at it in that way, the three variable fragment is clearly undecidable, right? Because FO3 is already undecidable. One variable fragment is always monodic and therefore is decidable from the previous slide. Now, the question is, what happens to two variable fragment? Note that the two variable fragment of FOML is undecidable, right? And therefore, the translation that we had clearly will not help. And in this talk, the rest of the talk, I will try to tell you a brief proof idea of how to prove that the two variable fragment of term modal logic is decidable. Now, when Volter and Zakharyachev proved that the two variable fragment of FOML is decidable, they say the following. So they say all undecidability proof of fragments of modal predicate logics exploit formulas of the form box psi xy, in which the necessity operator applies to subformulas of more than one free variable. In fact, such formulas play an essential role in reduction of undecidable problems to those fragments, right? Now note that this particular formula, box psi xy, is not expressible in term modal logic. Why? Because we are in two variable setting. This box should also have some modality associated with it, so, right? Some index. So we can only have either box x psi or box y psi. In general, box is not allowed if you have only two variables, right? And this is one of the crucial ideas to get decidability. Now, what intuitively it means is that if I fix the interpretation for x and y, let's say a and b, this box or diamond can only access either a successors or b successors. It cannot access any of the c or d successors, right? So for every other agent, it cannot access them. And whatever changes I do in those subtrees will not affect the formulas with respect to a and b. And that is the key idea to get the decidability. Now, the proof strategy to get the decidability is standard in the sense that we first have a normal form for the two variable fragment, and we prove a bounded model property. So let me just briefly discuss how these go. So the normal form is a combination of first order normal form for two variable first order logic and for the modal logic. Now for modal logic, Kit defined a normal form, which is a recursive DNF, which looks like this. It's a DNF where every clause looks like this. It has some finitely many literals, and it has one box formula and some finitely many diamond formulas, right? Now, what does recursive mean? Recursive means, look at this alpha and beta j, right? They're also in this normal form. That is what recursive means. So it's a DNF where each conjunct, each clause looks like this. It has some finitely many literals, one box formula, and finitely many diamond formulas. And whatever formula is there within the scope of the modality is recursively again in this form, right? For first FO2, we have Scott normal form, which looks like this: for all x, for all y is phi, and some finitely many for all x there exists y psi, right? So this is the famous Scott normal form for two variable FO. Now for two variable term modal logic, we combine the two normal form, and our normal form looks like this. We call it the fine Scott normal form, and it's a recursive DNF again, where each clause looks like this. Let me explain what this is. The clause is basically a conjunction of all this. What does it say? It has some finitely many atoms, predicates or negated predicates, and one box X formula, finitely many diamond X formulas, and one box Y formula, and some finitely many diamond Y formulas. And then we have for all x, for all y phi, and some finitely many for all x there exists y phi psi, right? And this part says when x is quantified and y is free, then we would have for all x gamma and some finitely many there exists x delta. And similarly, we'll have for all y gamma and some finitely many there exists y gamma or delta, right? And if you look closely, this whole thing mimics the first order normal form, right? And this whole thing mimics the FO2 normal form. And this intermediate thing, these two clauses basically mimic the case where one variable is quantified and the other is free. So if you know a normal form for one variable FO, this is how it would look like. So we treat the variable that is free as constant and get this normal form, right? Again, recursively, in the sense that this both alphas and beta j's should be in the normal form, and all these gamma deltas are quantifier free, phi and psi are quantifier free. And if there are modal formulas in them, they should, again, the modal formulas should recursively be in this normal form. So this is what we have. And what we can show is that any normal form any formula of two variable TML that you take has a equisatisfiable translation into this normal form. Now, once you have this normal form, we need to get a bounded model property, and the bounded model property is based on types. And in FO, typically this is how you would define types, right? So you say two type for two elements or two domain elements to basically be all the predicates or negated predicates that would be true when I assign x and y to these two values, right? Now for term modal logic, there are two things. One is that we cannot have a global two type. So at a world, we can have a two type for the given two elements, right? So we need to say two type at a world for these two elements, right? And along with the predicates, we also need to look at the modal formulas in the type information, right? So for instance, here you have by delta, I mean either box or diamond. So you need to look at either box X, phi, XY or diamond X, etc. Right? So for every combination of box or diamond with X or Y, you need to look at those formulas also in the type information. Now, how is a bounded model constructed? Now, this is to say that if you start with a formula that is satisfiable, you take that model and convert it in some way to get a bounded model, right? So now what is it that we do? Now, because we are looking at K frames, we can assume that the given model is a tree model, a bounded tree model, in the sense that it's of bounded height. Now, if it's of bounded height, we can go into the leaf first in the inductive step. And at the leaf, note that we only want to preserve model-free formulas, right? Now, what is a model-free formula? It's just FO2, right? Now, for FO2, we know how to construct a bounded model, right? So we can use the standard FO2 bounded model construction for that. Now, once we have that, we construct bounded models at the leaf, right? Now, inductively assume that you have constructed the bounded model for all subtrees for this particular root. And then what you can do is you can define a type-based model where you, instead of the current domain elements that you have at this world, you replace it with the corresponding types. And for all the successors, you do something so that you get a bounded model which you already have inductively, and you glue it in a particular way so that the monotonicity is preserved and you have a well-defined model, and thus you get a bounded model property, right? So you define a bounded model based on TML types and get this. And what you can show is that this bounded model that you get is double exponential in the size of the given formula. And therefore, this already gives a non-deterministic 2xp time algorithm, right? So the algorithm can guess the model and verify that it's true. To conclude, I just showed you that how we would prove that the two variable fragment is decidable. And this is crucial because two variable FOML is undecidable. And that basically tells us that these two are apart. Now, of course, there are other decidable fragments also for this logic by Orlandelli and Corsi and Stacksher et al. Right? So due to time constraints, I'm not going into that. Sorry about that. But just to conclude what I was saying, now we only looked at two variable without equality, without constants, right? So some of the operations that we have, first of all, if we have, as soon as we have one constant, we can have undecidability, because we can essentially code two variable FOML where the constant is used to encode the actual box. So we can do that. Otherwise, on the other hand, the equality is a more interesting case, because with equality, we can prove that it does not have finite model property. On the other hand, we don't know either to prove that whether it's undecidable or decidable, right? So the decidability is open, but we know that the current construction does not work because it does not have finite model property. And with respect to frame restrictions also, we do not have much results yet. So we need, so most of the things are open, like what happens with respect to various frame restrictions, whether the decidability holds or not. And note that when we looked at the translation of term modal logic to first order modal logic, in fact, it translates into the guarded fragment of FOML, right? Now, this leads to a natural question whether the two variable guarded fragment of FOML is decidable or not, right? So FOML two variable is undecidable. Guarded fragment is also undecidable. But then you can ask, where is the borderline? Does that mean the two variable guarded fragment of FOML is undecidable? And more importantly, the tools and techniques that we have developed for proving TML two variable TML is undecidable, can it be used for proving that the two variable guarded FOML is decidable? That is open yet, and that needs further exploration. So with this, I will stop, and thank you for your time. And if you have any questions, I hope I'll be able to answer online. If not, please address your questions to Jam, and he can answer all your questions. Thank you.